Chapter 7, Transverse Shear, Shear Stress Distribution in a Wide-Flange Beam. So in this example, we are plotting the shear stress distribution acting over the beam's cross section, which is a steel wide-flange beam with the dimension provided below, which is subjected to a 80 kilonewtons vertical shear. Mhm. And the dimensions are provided here. Let's see how we can get the shear stress distribution on an I-shaped section. Mhm. So if you look at the figure, you can easily see it consists of a web and the two flanges at the top and the bottom. So if we just consider the flanges, because they are identical to each other, I2 and two of them, and go the moment of inertia for web goes by a I1. So this is again web, and these are flanges, top flange and the bottom one. So the my assembly consists of web, which has I1 and two flanges at the top and the bottom, which goes by 2I2. So if I want to calculate the moment of inertia, at I1 goes by, that's a rectangle, 112 base cube height, and the height is 200, total height for web is 200 millimeters, and the thickness of web is provided 15 millimeters. So that's a base times a cube height, and that's just a conversion from millimeters to meter to the power of 4. And that gives me a 10 to negative 6 meter to the power of 4. And the other part is I2. I2 is again 112 base. Base is this time a 300 millimeters times height, which is 20 millimeters for each flanges. That's 20 cubed plus, and this time we just want to travel from any other axis to the neutral axis or centroid. So to the center, that's a positive plus 2AD. 2 area of flanges is 20 times 300 times d is just the distance from the neutral axis for entire shape assembly, which is here, and that's 100 plus the height of flange is 20, so centroid is lies at the center, so that's simply a 110. That's my d. That's d squared, and that's the conversion. It just gives you the numeric value of if you add I1 plus 2I2, which is I total, that's I1 plus 2I2 web plus two flanges. It gives you I, which is equal to I total, and that's a 155.6 times 10 to negative 6 meter to the power of 4. That's just calculation of moment of inertia in shear equation. And let's see what do we have here. So for example, let's consider a point like B prime. Just this much higher than the line which separate flanges from web. So if you go a little bit higher than this line, you will be on flange. And if you just go by a small amount of height lower than that line, you go in web. That's the difference of B and B prime. Let's first go by B prime. Mhm. So in web, in flange, when you move up, you are in flange. So the thickness is 300, mhm, equal to B. If you remember, it was 300 millimeters. Mhm. So one can say, and QB prime is also Y bar prime times A prime. Mhm. So how that goes? That's 110 times 300 times 20. So just assume like this. This is my flange, mhm, by the area of 300 times 20, mhm, for B prime. Mhm. The area which V prime locates at times 110 times what times where times the location of centroid of top flange to the neutral axis of entire system. So this is 100, this is 20, so center is just 10. So that's 110. Mhm. And if you do the math, it gives you a numeric value of 0.66 10 negative cube 10 negative 3 times meter cube. Mhm. And if you calculate tau for B prime, it gives you V times QB prime over I for entire system, which we already calculated, times thickness of B prime. So B prime, as we already discussed, is on the flange side. So that's in the flange side of our problem. So that just go by the thickness of flange. That's a 300 millimeters. Mhm. At B prime, we are in flange, so the thickness which shear applies on that is the width of the flange, top flange. So if you replace the numeric value, a shear is given, which is 80 kilonewton times QB, which we just QB prime, which we just calculate that over I for entire area, which we calculated in previous slide, and times 300 millimeters convert to meter, 0.3 meters, and it just gives us 1.83 megapascal for point B prime. Mhm. Let's let's see what if we just come a little bit lower than the separation line, which enters us to the web, and uh, that's point B. Let's consider what happened in B. So as soon as you just climb down a bit from the separation line, now you are at web. So the thickness goes by the thickness of the thickness which V vertical shear applies on that goes by the thickness of web, which is 15 millimeters. Do you remember that from dimensions? But the Q remains the same for both of them because that's almost at the separation line. So it just still goes for the amount of area or moment of first moment of inertia, first moment of area for the top flange. So QB remains equal to QB prime. Because you just climb a bit lower than the area, so area remains the same, but the thickness for shear change. So how that goes? Tau B, mhm, tau B V remains the same. I for the entire assembly remains the same. QB prime remains the same. The only change here is the thickness of a part B. We can easily expect to have a much higher shear due to a reduction in thickness from flange to web. Flange is wide, coming down to a thin web. It just gives you a small thickness, and it just drastically increases the shear at B. So if you replace the value, it just gives you a numeric value of 22.6 megapascal, which in comparison to 1.3 for previous section is a much higher. Let's see, investigate another point, something like C, mhm, at the center, which lies at the centroid here. So in that sense, at C, QC it's nothing but summation of the area from the top to that point. So that includes a two part. The first part is a flange, and the other part is half of the web, mhm, area to the centroid. So that's a summation of y bar prime a prime, which gives you a which gives you a 300 times 20, a 300 times 20, which is the area of 1, mhm, times y bar prime, which is again 110 to the centroid for the first part, and plus 100, which is this height, mhm, the area 2, times 15, which is the thickness, so that's the second rectangle, half of the width, times 50, which is the centroid of what? So one is centroid for the first part, and the other is centroid for the other part. So this is 50, this is 110. This is 50, this is 110. Mhm. And if you do the math, it gives you a numeric value of point 735 times 10 negative to the power of 3 meter cubed. Mhm. And if you plug that in tau c, which is by the intuition, that's a sine of tau maximum. Why is that? Because do you remember tau either happens in the smallest thickness or maximum area, and to the center, like the circle problem, which we just consider half of the area, and this is the half of the area as well. So that's a hint to maybe that's the maximum shear. Let's verify that. And if you plug in the numeric value, it just gives force remains the same, total I remains the same, thickness goes by the thickness of web, and that's Q just comes from here. Mhm. So we just replace a numeric value of Q from here, mhm, to our equation. And if you replace the numeric value, it just gives you a 25.2. Mhm. And that's a higher value than the last two previous two values. So what we have done so far, we just go by a 2 point at the separation line. One is B, the other is B prime. One is smaller by this much higher than the separation line, which is that goes by B prime, and that stands in a flange, top flange, and B is just a smaller amount lower than the separation line of flange and VIP, and that stand in the VIP. So that goes by the thickness of VIP. And then the other one is just a point C which lies at the centroid. Let's see if we want to observe them. It just gives us tau B prime is 1.83 megapascal. Tau B is far higher due to change in reduction in thickness from flange to web increases the tau drastically. Mhm. And when it comes to tau C, you can easily see that's even higher than B. That moves from 22.6 to 25.2, which is megapascal. That's a tau maximum, and that's a interesting uh, study for a I-shaped beam which you want to if you want to uh, draw the shear stress distribution. It just says the minimum are at the start of end of the two flanges, and that just goes by a numeric value of 1.3 megapascal in our example, which we already calculated, and it just drastically increases as you enter from the web from the top flange to the web. So if you just move from B prime to B, it just shear stress, it just goes from 1.3 all the way to 22.6 megapascal. Yet it increases, but by a smaller amount to reach to the maximum amount of shear at center or neutral axis or centroid, which is 25.2 megapascal. And that's again decreases because it's asymmetrical and reaches to the same amount of tau b, like tau b at the top, and reduces to as it enters to the lower uh, flange, it just reduces to the 1.3 megapascal. And that was an interesting observation in the distribution of shear forces in a wide flange I-shaped beam. One can say the larger shear stress occurs in the web, and it's almost uniform through its depths, almost uniform because it's still changing, but it just changed from 22.6 to 25 in comparison to the numeric value of flanges. It's you can say 22.6 variation to 25.2. It's almost a uniform changes. Mhm. And that's varying from 22.6 megapascal to 25.2 megapascal, and that's the reason of why some of the codes allow you to go with the average shear for design. And what that means, it just says for just go for the calculation of web average shear for web rather using the shear formula, and that's far simpler. And but that's again that's some codes allow you to go that way. And what is that? That's tau average based on whatever numeric value of your shear over the area of the web without the calculation of q, without the calculation of moment of inertia. Just simply divide the numeric value of your shear, which is provided by 80 kilonewton, over the area of web, which is 15 millimeters times 200 millimeters. That's the area in but just in meters in consistent unit. So that gives you 26.7 megapascal. And if you make a comparison between 26.7, which just simply comes from average shear just from the web to to the maximum shear of 25.2, that they are very close to each other. So one can say, even if that's not acceptable for all the codes, but that's a very good verification because the answer is very close to the the entire process of calculation of shear flow in a I-shaped beam. That's a comprehensive example of what happens in, and that tau average is 20.6 just based on the web. And that's why some codes allow you to go that way. Mhm. Again, that was a shear flow distribution, and thank you all.